Now paste in the chat. This machine is going to die anytime soon.
That's a laugh way to come on.
How long do you think that will take?
I don't know. I'm picking carpet now.
Okay, it's a good sign. I could use this. Of course, we don't have the sign of education thing here.
I know.
You want to test the mic?
Testing, testing.
Wait.
Oh,
You can test it.
okay, testing, testing, etc.
Doing something. It's a slower. Now?
Testing, testing. 1, 2, 3.
Okay. Oh. You can test now.
Okay. Yep. Hello, testing, testing.
Nothing.
You see, last week we had to like disable it and re.
Yeah, that's what they did initially.
Just click on
Okay.
it.
Oh, now I think it's speaking. You see that? Right?
Yeah.
I don't know if yours
Testing,
might.
testing.
Okay, let's try one more time.
Okay, testing, testing,
No,
etc., etc.
no, it's not recording. No.
Oh, testing, etc., etc.
Oh, I know we are pushing you too much, but you can do it.
It is only Windows.
I hope it records.
I'm not sure what we did.
Let's paste the thing. So after the hangout is done, bring up Camstation. Where do you think I should put this? I send an email to courses or put in the wiki?
Sorry, what? The
Like,
instructions?
yeah, for
Oh.
doing the whole process.
Yeah, put it in the wiki. Or the track.
The trash. chat. Enter the checks. Okay. So initially you should be ready. First thing you need to do is start the recording.
Okay.
We'll check that the sound and everything is okay.
Yeah.
So you down here?
Yeah, I think they've got us somehow.
Yeah. Good. Yeah.
So using this over using looks and this great points. Yeah, I feel so. Yeah. I think it's up to explain this. Well, on that topic, I just came across this. Well, this is different, but there's a new thing that just came out called YouTube. Just using that for the cool thing is that you can run like multiple cores. So and it does model testing and implements like within the code. You don't have to do so. -3.
Okay. So do I just hit this?
Yep.
Okay.
Do a little test just to make sure this one picks up the right.
Right.
And it's
Okay. Testing.
yep. F10. Press F10. And another test part.
Oh. Okay, I think we'll get started. Okay, so today we're going to talk about using Numpy and Scipy and doing numerical and starting to do numerical analysis with Python. Possibly. Okay. Numpy is a package providing arrays, standard numerical arrays for Python, and Scipy is sort of a meta package. And the stuff we'll talk about today is linear algebra, statistics, and polynomials that are part of Scipy. This is just not. Oh, no, now it's working. Okay. Okay, so up to now, you've been using lists as your sort of data type. You know, they look sort of superficially like vectors and matrices, but they're not. They're not the ideal type to do numerical analysis. And the reason they are is because they're more actually like, they behave more like strings than vectors and matrices. And you can see this here. So I'm going to define two vectors, or what look like vectors, A and B, two lists. But now, if I say 2 times A, what I'll get is 2 copies of A appended to each other. And if I do A plus B, I get the concatenation of A and B. And like I said, this is because lists are behave more like string types than numerical arrays. So what we need is so numerical arrays do not come standard with Python, so you need a separate package to provide them, and that package is Numpy. And so here, so you get them. So from Numpy, we'll import a few functions here. One called zeros, ones, and zeros just creates a new array with all the values initialized to 0. So if I call zeros 5, I'll get a vector of 5 elements, all 0. And likewise for ones, it'll be an array with all ones, with the dimensions I specify. Now here in this example, I've also set D type, and this sets the type of the individual elements. So it defaults to double. But say if I want an integer array, then I would just pass in D type int equals int. Okay, so that's zeros and ones. Now the other usual sort of way to initialize arrays is to have, say, an increasing sequence of values. And one way to do that is with a range. So a range is like range or x range, just that it returns an array instead of a list or a generator. So you say a range 5, I'll get an array with the value 0, 0 to 4. And the other way is if you want, so this is good. So this is good for if you want integer values, but if you want, say, a sequence of float values, then you can use linspace. In linspace, what you do, there's 2 or 3 argument versions. The first 2 arguments are the start and stop points. And then the third argument is how many points you want, which defaults to, what, 50? Yeah. So for instance, if I just do 1 to 5, I'm going to get an array of 50 elements starting at 1 and ending at 5, equally spaced. But here, if I do 1, 5, 6, then I'm going to get 6 elements, also starting at 1 and ending at 5. Okay. So far, so good. Now, you access the elements just like you do with standard lists, just by using the square brackets. Indexing starts at 0. Also like lists, but unlike, say, MATLAB, if you're used to that. And just a note about the memory layout. This is what the memory layout is. What's called row major, not column major. And so as the slide says, yeah, C++ Mathematica to use row major. A lot of other numerical languages like Fortran, MATLAB will use column major. It's just keep it in mind, because it can really affect your performance if you access the array, if you access the elements out of order or out of sequential order. Okay, so as I said, indexing starts at 0. So now here in the previous slide, I made just vectors by passing in a single value to array to zeros. But if I pass in a little list, I'll now get an array of 2 rows and 3 columns. And then I can set some of those elements here. So this is the first row, second row. So here, the second row, third column, because remember indexing starts at 0. I'll set that to 1, and then set the first row, second column to 2. And if I print out A, I can see that's what happened. And if you try to access elements outside of the array, you'll get an index error. So this is different from, say, C, where if you just access outside the array, you'll just get a random spot of memory. It won't actually throw an error. And anyway, so the error message is pretty clear: index 2 out of range, and it says what it has to be. Okay, so now copying arrays. It works the same way as lists and dicts in Python or other sort of complex types. If you assign, assignment doesn't create a new copy. So if I have an array A, little two-dimensional array, and then I say B equals A, what I've gotten is now a reference. B is a reference to A. It points to the same spot in memory. So they behave exactly the same. So if I change one of the elements in A, print A out, see it's changed. If I print B out, I'll see it's also changed too. Because B is just a reference, it's not a new copy. So if you want to copy, you can use, say, a.copy to get a copy of the array. But like I said, this is the same behavior you'll see with lists or dictionaries or other types in Python. So it's consistent. It's consistent there. Does that make sense? Okay. So yeah, the reason we have this type is not only efficient layout of memory. Since lists can store anything in Python, they're quite heavyweight. Each element is basically, can point to anything in memory. So it's very inefficient to actually go through these arrays. So that's one reason to use them. The other reason is that we can actually do real matrix arithmetic and not treat them as like a string type. So okay, so I'll make a little array with a range. And now if I add 3 to it, you can see I'll get the expected result, right? If I multiply the two together, so now I've got 2 vectors, A and B, same length. If I multiply them, what I get is a new vector with the same length as A and B, which with the elements that it's on a per element multiplication. All right, so the first element is just the first element of A times the first element of B, etc. And C here is just a scalar, so if I just multiply by that, I get the expected result. Just multiplies all the individual elements by the scalar. Okay.
Sorry, one question.
Yeah, sure.
I'm sorry, maybe I got confused, but you said it has array and then 3-point comma. Why it has a point?
Oh, sorry. Here?
Yes.
That just means, so, okay, so if you look at this type, it's created an array, an array of integers. And here it's created an array of doubles. So 3 dot is just a double with the value 3. And this would be an integer. 3 is just an integer with the value 3. Yeah. Okay, so yeah, so if you do arithmetic operations with arrays, the multiplication, the addition, the division, etc., happens per element. Now that's so that's not necessarily what you think might happen. For instance, if you multiply a matrix by a vector, you will not get matrix multiplication. So here I've got a 2D array, 2 by 3, and I'll have a little vector B with the same number of columns as A. So A is 2 by 3, and B, the dimensions of A are 2 by 3, and the dimensions of B are just 3. So now if I multiply A by A times B, now if this was matrix multiplication, that would raise an error, right? Because the shapes wouldn't be correct, right? But you see what happens actually is I get, basically, what happens is the system says, okay, I'm going to do a per element multiplication, but because the sizes don't match, it's going to pretend that it's basically just going to replicate B for each row that it needs. You see it's basically multiplied the first row of A by B, and then the second row of A by B, by another copy of B. So yeah, so what this is called is that it's the per element operations broadcast, in the sense that any dimension that missing dimensions or dimensions of length of size 1 are treated specially and are just copied if need be. But you're not getting the answer that you might have expected, which is standard matrix multiplication, i.e., you're not getting a new vector from A and B. Okay, so how do we do matrix multiplication? Here, what you have to use. Oh, sorry. Before I talked about that, so that was matrix vector. Matrix is similar. So here, if I have two matrices that are the same size, the elements, and I do A times B, then I get a result which is just the per element multiplication of all the elements of A and B. But I don't get the standard matrix multiplication result. Okay, so how do we do matrix multiplication? And that's two ways. There's the dot function, which works everywhere, but there's also the brand new @ sign operator, which came out in Python 3.5, so the latest version of Python. So we'll use dot here since it works more common. But in the future, keep in mind that there will be a special infix operator to do this, so it'll be a little more convenient. So so what you have to do, so I'll make two matrices, A and B, 2 rows, 3 columns. And now there's I can do a transpose and take A and turn it from 2 by 3 to 3 by 2. And then use the dot function to do matrix multiplication. So now I've got A transpose times B. This is 3 by 2. B is 2 by 3, so the dimensions line up. So I'll get a 3 by 3 matrix out. And if I swap, so now do B times A transpose, now I'll get a 2 by 2 matrix out, because the inner dimension was summed over. And you can do this with vectors too. So now if I do A dot A and C, where C is just a little 3-element vector, then I'll get a 2-element vector out. Let's multiply the matrix by the vector and produce a new vector. Okay, and as I said, in the latest version of Python, you could write this as A at sign C. Okay, any questions on this? Okay, so that's basic array types in Python with the Numpy module. But typically, when you have these types, then you want to do some linear algebra on them. It's obviously very inefficient to do it in Python itself. So it comes with all the typical functions, inverses, determinants, norms, etc. You know, you can do eigenvalue decompositions, SVDs, Koleski, etc., etc., etc. So now both Numpy and Scipy have a linear algebra module, but Scipy's is compiled against a BLAS and LatePack, which is a optimized numerical library written in Fortran. So it'll be much more efficient than the Numpy version, typically. Okay, so I can import, so now instead of from Numpy import, I'm going to do from Scipy import dot and linalg. And I'll make a little 3 by 3 matrix here and take the determinant. So linalg dot det A, i.e. give me the determinant of the matrix A. And now here I want to take A and multiply it and do a matrix multiply with the inverse of A. So I use dot for matrix multiply, so dot A, and then use linalg dot inv to create the inverse matrix, right? And so you can see here that I've got ones on the diagonal, but because this is floating point arithmetic and it's not exact, I have very small values. So most of them are 0, but I get a small, 10 to the minus 16, 10 to the minus 17 values off the diagonal. Because you can't do exact, this will be done just in floating point, and you can't do exact calculations. Okay, so we've got little round off errors here. Okay, so one of the more common uses of the linalg module is to solve systems of equations, i.e., instead of doing, so you can see in the, we can take the inverse of a matrix and multiply that by a vector to solve, but that's typically very inefficient and numerically unstable. So the better way to do it is to use the solve function to solve this system without inverting A. So I'm going to have a little 3 by 3 matrix A and a little 3 vector B. And so instead of doing, linalg.inv A, and then multiplying that by B, I can use linalg.solve with A and B. And this will then solve for X directly without inverting A. Then I get out what should be the right answer. Okay, so any questions? So that's just a brief tour of the linalg module in Scipy. Any questions on this before I move on? Okay, so as I said, Scipy is sort of more of a meta package. Creates a lot of sort of contains a lot of useful scientific packages within it. One of them being the stats module, and which contains basically all the statistical distributions you'll ever need, most likely. Comes with pretty much every distribution you've ever heard of and a bunch you haven't. Normal, Maxwell, something called Gumbel, left skewed, etc. And there offers two flavors of distributions: continuous and discrete. Continuous, the standard example being the Gaussian, and discrete, like a Poisson distribution. And for each of these distributions, it comes with a series of functions that let you do various things with it. Compute the continuous distribution function, mean, variance, etc. Okay, so now I'll just show you an example of the normal distribution. So all the continuous distributions take two parameters called loc and scale to adjust the center and the width of these distributions. And the defaults being 0 and 1. So I'm going to import norm from the Scipy stats module and make a little vector of values. So remember, linspace, this creates 100 values between -5 and 5. Okay, now I'm going to plot the values x, and then the y values are norm.pdf x. So the probability distribution function of the normal distribution. And again, because I haven't set any value, because I haven't specified loc and scale, it defaults to 0 and 1. So you can see, yeah, centered on 0, and 1 sigma is 1. Okay, but if I change, so now I can pass loc, change the mean to 1, does the right thing. Or set it to -1 and then, increase the width to 2. Okay. Now, typically you'll have, you want to compare these distributions with data. So there's a hist function in the PyLab package. So from PyLab import hist. Okay, but continue back on the various functions within each distribution. So I can now calculate the mean. So if I say norm mean, with these various parameters, it'll basically just return log. STD is the standard deviation. So that's the scale parameter. I can get the third moment with this moment function. And then now I want to sample from this distribution, right? So before, these are just sort of, these are parameters of the distribution, but now I want to start actually generating random samples. And so that you can use the function called RVS. So random variate sample. I think it's the acronym. Okay. So this first parameter size is how many samples I want. And then again, I can pass the other options to change the distribution, so loc and scale. Okay, so I'm just saying I want 1,000 samples of a Gaussian centered on -1 with standard deviation 2. And now I can use the hist function to now bin up these samples I generated and see that, yeah, I'm getting roughly the right thing. Okay. So now I can overplot the distribution again using the PDF function. I don't know if you're not familiar with this extra options to plot. R here just says make it red, and I think line width is self-explanatory. Okay. So that's an example of the continuous distributions. So they also come with like, as I said, the discrete distributions. Here's an example using Poisson. So again, I can calculate various parameters. So here, the Poisson, remember, only takes basically one parameter. So I'm just going to characterize it by that one parameter 4. So I take the mean and the variance. You see they're the same. So, but for the discrete distributions, instead of PDF, there's called it's the PMF function. It's the probability mass distribution. And here, the options of the plot here, O and dash means draw a circle at each point and connect them with lines. Okay. And I can also plot the continuous distribution function. Any questions on this? Okay, so that was just a brief tour of the stats package. So there's a bunch of stuff in here. We're not going to go through everything, but just sort of a little tour to get you started. Another package being Poly1D for doing symbolic polynomial manipulation. So remember, with the the example of the matrices and multiplying the inverse together, you're subject to round-off error because it was all the calculations could be done in floats. But here we if we want to do polynomial manipulations, I can do that without floating point error using this package. So here, I'm going to use the Poly1D function with the arguments 2, 2, 3. And what this says is give me a polynomial with the first coefficient 2. So this is the coefficient of x squared. This is the coefficient of x, and this is the coefficient of 1. So if I print the result, it's going to give me the polynomial this function represents. So 2x squared plus 2x plus 3. All right. So the number of elements here tells me the degree of the polynomial, and the values are the coefficients of the polynomial. Okay, so I have this p object. Now if I can use it as a function to evaluate the polynomial at specific arguments. So here, p 1.2, I just get 8.28 out. This is just evaluated numerically, right? And p.c just gives me back the coefficients I used to construct it. And I can, so these are polynomial objects. You can multiply polynomials. So here I'll make another one, multiply them together. So this is a polynomial of order 3. This is a polynomial of order 2. So I'm multiplying them together, taking the order. Obviously, I'm going to get 5. And I can print out the result here. Okay, so one of the nice things you can do is now that I've got this polynomial, I can say, well, what are the roots of this polynomial? Factor this polynomial for me by just calling this q.roots, and I'll print out the 3 roots of q. Remember, q is order 3, so it's going to have 3 roots. And so the j is and as you can see, the roots here are complex. So that's what this j here means. Any questions on this? Okay, so now we'll talk a little bit about fitting polynomials to data. So here I'm going to import the polyfit and polyval functions from Numpy, and also use the random module to generate random numbers. So okay, so here's where I'm going to here's my x values for the data I want. Now I'm going to generate random values for y here, which is just I'm going to give it a linear slope, and then some random noise around it. So that's this 50 times r here. Now, people understand this bit. I'm taking r equals, just for the purposes of this slide, I'm taking r equals random.random. This is a function. And now I'm just calling the function here. And I'm just doing this just because otherwise it runs off the slide and you can't see it. So, but if you're unfamiliar with this, you can assign functions to values and then call those names later. Okay, right. As I said, y is just x with some noise added to it. And now I'll plot them. And again, O means plot with dots. And you can see, yeah, noisy, but yeah, with a definite linear trend. Okay, so now I want to try to fit a polynomial to this data with the polyfit function. So again, the arguments are x and y, values of my data, and then the order of the polynomial I want to fit. So I want to fit a linear slope to this, so that's a 1-degree polynomial. And it'll give me out a little array of the coefficients it fit. And now I can plot this using the polyval. So plot x, and then evaluate the polynomial at all the values of x. So the first argument is the fit coefficients, and the second argument is all the x values I want to evaluate it at. Okay. And I can keep going. So I don't know. I mean, I've constructed the data, so I know exactly what the true model is. But you don't necessarily know that. So let's try a second-order polynomial. Again, all I have to do is change the 1 to 2 here. Get a 2-degree 2 polynomial, and then plot it over.
Mike, the fit is in the least square sense. What does it do?
I mean, it's doing a least squared fit. But details wise,
no, but that's the
yeah,
limitation.
right. No, that's a good point. Do people know? Everyone know what a least squared fit is? It's just minimizing the difference between the model and the point, and taking the difference, squaring that, summing them, and minimizing that function. Okay. I think we're going through pretty fast. What time is it? Okay, so as I said, this is just a brief tour to get you started. There's a Numpy tutorial here, a tentative Numpy tutorial, and Scipy has a lot of stuff in it. A good place to start is here. And okay, so we'll just move on to summarize and then talk about this week's homework problem. So yeah, so when you're manipulating numerical data, you want to use the array type, not list. Remember that array types, if you use the standard numerical operators, you will get per element, addition or multiplication, etc. You won't get matrix multiply. So for that, you have to use the dot function or the new @ operator. Scipy comes with a fairly complete set of statistical tests, functions, all sorts of neat stuff in there. And yeah, so we'll talk about the homework problem for this week. So we talked about, remember, version control in the last lecture. So want, will want to see not only just the solution to the problem, but also your Git log, or your Mercurial log. We don't have to do anything fancy. Just make a commit, and just to show that you've used it and you've gotten the basics down. But yeah, since this is such a small problem, you don't need any fancy. You don't need 10 commits here, right? 1 or 2 commits is fine, right? Okay, so the problem is I've got two variables multiplied together. Each of those variables is drawn from a different distribution. So A and B. A is going to be drawn from a normal distribution. B is going to be drawn from a uniform distribution with these limits. And now I'm multiplying together, and I'm getting I'm sampling essentially from a new distribution. But we're going to have you write a program to just generate 1 million samples for A and B, find X, and then just plot the histogram of X, right? And just see what is the distribution of X. And then you're just going to see, so you're going to have to save the figure with the savefig command and send that to us. And using the histogram, find what's the most probable value of X. Does that make sense? Okay. Just very simple. Mostly this is just, just getting you used to this stuff. And then the second part of the problem is we're going to use that poly 1D package. The poly 1D package to solve for this polynomial. Okay, so I've got a 4th order polynomial, but the coefficients, 2 of the coefficients are related this way. So what we want you to do is plot the roots of this polynomial as a function of, I never remember what this is called, psi?
Zeta.
Zeta, yeah, okay. And to keep it simple, only consider zeta less than 0.62. Otherwise, the roots are going to go complex, and that's just going to mess. It's just slightly more complicated. So keep zeta less than in this range, and then all the roots will be real. Be easier to work with. Okay, and we just want a plot of the roots of this polynomial as a function of zeta. Does that make sense? Okay, well, that's it for me. Any questions on this or the homework last week, or?
So we can use Git, right? We don't have to use Mercurial.
Yes, you don't have to use Mercurial. You can use Git if you want. Yeah.
Just want to mention for this group that there's an intro to the Linux shell next week. So if you're kind of new to the command line 2, which we're not using here, but if you're curious, it's a very basic introduction to what you can do on a command line. So that's next week. I forgot exactly the date, but it's on the education website.
It's probably Wednesday, right?
Probably.
Yeah.
And homework's due today. That is the due date. I want to remind you, you can submit it late, but there's a half point every day that it gets taken off. So if you have questions, try and ask them today to not lose the points. Okay.
Oh, whoops.
No, don't delete them. No. Everything got deleted.
Okay.
Right. Okay. Mhm.
So let's say
Right.
50 pounds. That's really want to.
Yeah, that works. Well, it amounts to the same thing, but yes, sure.
So for I in that range, I is equal to the value return 5.